Good morning, participants. On behalf of VEL and Department of Civil Engineering, I welcome you all once again for this 6-day FDP on recent advancements in geotechnical engineering and industry perspective. So in this 6-day FDP program, we are calling experts from various industries. Yesterday, two sessions got completed, and today we are moving on to the third presentation. Our third speaker is Ms. Gauri Krishna, who is a marine geotechnical engineer at Covi India Private Limited. Prior to this, she has worked in AECOM for 5 years, specializing in analysis, design, and review of infrastructure projects. Her key contributions includes critical roles in projects like Greater Malay Tilafushi Link, Myanmar Yangon Yard Container Terminal, K-Ride, Corridor 3 Chennai Metro, and many other things. And she is also an expert in soil and rock mechanics, ground improvement, slope step design, and foundation engineering. She is also an expert in GeoStudio, Group, L-Pile, Rock Lab, Plaxis 2D, Flac 3D. And ma'am has obtained her MTech from IIT Madras. We welcome you, ma'am, for the session.
Yeah, thank you. Good morning, all. Yes, as ma'am has introduced, I am a geotechnical engineer. I am Gauri Krishna, and I have almost 5 years experience now in geotechnical engineering in various projects. So today in my presentation, we will talk. I will take you all through one of the project I have done, and let's discuss it together. I am audible, right?
Yes, you're audible.
Okay, then I will start the presentation. Is there any time limit as to how much time for presentation, how much time for Q&A, anything like that?
Last 15 to 10 minutes we can devote for Q&A.
Okay, so I have time till 11:30, right?
11:15.
11:15.
Yes.
Okay, okay, sure, sure. Thank you. I will share my screen.
Yes. I have made you co-host. You can share it.
Okay, let me know if the screen is visible.
Yeah.
Okay.
Yes,
Uh,
visible.
1 minute. Uh, is the slide available fully or is it like
It's not in presentation mode. PPT screen is
okay?
visible.
Okay, then in that case, stop sharing. Uh, is it visible now in presentation mode?
No,
No.
your folder is visible actually.
Uh, okay, I'm able to share only what is open, sort of. When I click on the
Yeah, when you do it
presentation,
in Google Meet, you can share your full screen only.
actually, I have three screens, and in one screen only this presentation is coming. So in that screen now, file is open. That's why that is getting visible. And when in that screen presentation is coming, it's not. Mm, maybe let me try once more. Now you are able to see just not in slide PPT slideshow mode, right?
Not in slideshow mode, but we can see the screen.
Okay, let me.
Ma'am, pardon.
Ah,
Can
yes,
I
please.
answer here?
Uh,
Below the whatever the screen we have, it is visible to us. Below
uh,
that, we'll have a symbol. Just click on the symbol so that you'll be getting in a presentation mode.
yeah, yeah, I am doing that, but what is happening over here is my presentation is happening in a different screen. Let me make it into this screen it's alone, then it will be fine. PC screen only.
Yes, ma'am. That is thing.
Hmm. Yeah. Now,
Now
hello.
it's still in. It's not come in presentation mode.
Oh, is it so? It has come for presentation. Oh, you sorry, it's taking a lot of time. Hmm. Now,
It's still in the same.
but it has actually slideshow has started for me, so I don't
For us, it
understand.
is in the project overview slide is there, but it is in presentation mode.
Let me know if the slideshow is visible.
Actually, your screen is visible. Ah, yeah, yes.
Yes,
Now
ma'am.
slide
Yes,
shows.
ma'am.
Okay.
Right now
Okay,
it's
okay.
okay.
Thank you.
Yeah.
Thank you for the
No
patience.
problem.
Yeah, we can go through the presentation.
Yes, ma'am.
Yes.
Over to
Yeah.
you.
Hi, all. Yeah, yeah, sure. Thank you. Hi, all. So today I would be presenting
Ma'am, can you,
about.
sorry to interrupt, can you
Yes.
click on to that hide actually?
Oh, yes, yes, sure. Okay. So today we will be talking about specifically a bridge project, and in this bridge project, the ground type was coralline rock formation, and the pile design was bored pile type, and the standards followed were BSEN. BSEN is basically British standards as per European norms. So let's go through each of these terms one by one. I will try to be as simple as possible. And if any queries, you can keep it in, note it down, and let me know at the end of the presentation. So, as I told, this is regarding a bridge project, and this bridge is located in Maldives. And as you can see, mm, as you can see, what is happening over here is we have four islands. This Male is the capital of Maldives. Then we have Willingili, Gulhipalu, and Tilafushi. Most of the people reside in this particular island, which is very densely populated. And now, what Maldives government is trying to do is they are trying to expand the usage of their other islands. Maldives is basically a combination of some 22 to 26 islands. So what they want to use is they want to use the area of other isolated islands. So they now have only ferry, this ship sort of transportation now between these islands. So for that purpose, they were proposing a bridge, and countries like China and India are funding for these projects. So what will happen is, when such projects are funded, Indian companies will be designing and will be the contractor for that project. And that is how me, when I was working with AECOM, I had the opportunity to be the geotechnical engineer of this project. So when these four islands are connected using a bridge, and this is just a span of 6.7 kilometer, and we have in this a combination of marine bridges. By marine bridges, I mean the portion of the bridge above the water, and then we in these marine bridges itself we have three navigational spans. Navigational span means the portion where the land is, the seabed level will be dredged out, means the depth of water in that particular location will be very deep, so that the ships can pass through, ship or boat, whatever it is, it can pass through under the bridge. You also would have noticed in some bridges where two piers will be in a bit more distance than the adjacent piers. So why that purpose for that is that the piers are so far away that a bridge can pass through it. So what will happen, that navigational spans with wider set piers would be very much critical in the design, because the load coming into those two piers will be huge. If you think about it, when we have something to be supported and when we have the supporting columns or piers adjacent to each other, the load getting transferred will be less. But if it is kept far apart, then the load coming onto it will be for a wider portion and it will be high. So navigational spans is a critical part of these marine bridges. Then we have upgrade road or embankments. Means in this portion you can see a small yellow portion, right? And over here also peripheral to the island, over here and over here we have upgrade. Upgrade means ground level. Ground level also we have portions. Then we have interchanges and reclamation. What will happen is, for making the bridge at grade level, means at the ground level, sometimes there won't be any ground. That is what is happen, what will happen in this Malay islands actually. We will be taking a bridge in this fashion, okay? So when we take it in that way, we won't have any ground over here. So what we will do is we will reclaim the land. We will reclaim the land and we will put, um, like we will put the fill material, we will call it as fill material. We will put it in this water portion, layer by layer, and we will bring it to the ground level, and then we can easily take the bridge through the ground level. That is called reclamation. Now I want to show you a video of this 3D rendering of this project so that you will get an idea. Yes, so what we saw till now was four islands and the embankments, upgrade stretches, navigational spans, and all these things spanning through four islands. Now let's see what was the geotechnical scope for a bridge project. When we think about a bridge project, what would be the role of a geotechnical engineer? Let's go through that. So, in all of the projects, this is not a geotechnical thing alone. When a project starts, what we need to do is something called as deck study. In deck study, what we will do is we will check the site history. We will check site history, meaning it might include things like did an earthquake happen over here, or did any ground improvement happen before over here, such things. Then did any reclamation happen over here? These are all a part of site history check. Then we will have regional geology, like what is the ground type over there. Then what is the project requirements for this project? What are the requirements, like which code to be used? Is there any limitation on the pile type, like you should do only bore pile design or you should do only driven pile design? uh, and any budget requirements, all these things is a part of desk study. Then we will have ground investigation, then geotechnical design. After ground investigation is done and we have all the lab test or institute test results with us, we will be doing the geotechnical design part. So before doing geotechnical design, for example pile design, before doing that what we need to understand is what is the ground actually. Thereafter, we will have to look into any ground improvement required, or is there any liquefaction risks, cover erosion mitigation. Don't be scared about all these terms. I will go in detail about all these in later slides, and it will be ending with a pile test validation. See, what is happening is we will design a pile, okay, and we have to ensure at site that it will have the required capacity. So for that purpose, we need to do at end a pile test. Now let's look into the first scope, the desk study. So in the study, as I said about the site history, let's see how we did a study for this project. So what we first went and did is we looked into the Google images of the Malay Island. Now we looked into all four islands, okay, but now I'm showing you only for Malay and Gulhi Falhu. So in 2005, 2016 and 2017, you can see the development, how it is happening. In Gulhi Falhu, it was just like a lagoon sort of an island initially, which started reclaimed in one portion, then the reclamation extended in this fashion. And now, recently, when just I was preparing this presentation, I was looking into how it is looking now. So, this is how it is looking now. The image quality also has improved, and you can see in Gulhi Falhu some construction also has started. So what will happen is this portion will get sink down, sink down, sink down, and over here these coral reefs will come and form. So coral reefs will come and it will get deposited, and it will rise above the ground level. And when it raises above the ground level, slowly some plants and everything biodiversity starts emerging over here, and it will form a ring shaped island. So that is how this Maldives atolls has formed. Now coming to coralline rock formations, as I said, these are all some pictures. You can see some porous coral form. As it ages, it will become harder and harder, and that is what you see over here. So coralline rock formation, the major thing is it will be of carbonate content, and it is actually skeletal remains of marine organisms and primarily corals. So some examples of such rock formations is coral, limestone, and calcarnite, and these two were the part of this project geology also. And the property will be like it will be highly porous, means so many pores will be there, and it will be permeable. When so many pores are there, interconnected pores are there, permeability will be really very high. Permeability is basically the capacity of water to flow through these rocks, and it will have variable strength and cementation also. Like in this portion, when pores are less, strength will be more, but maybe in this portion pores are more, strength will be less. And we have so many this pores, they call as cavities also. Like what will happen is when we go into the underground, when the pores are in multiple in nature, that portion alone there would be like voids. There will be no rock formation, and that is called cavities. This is some example of coral limestone, how it looks, and calcarnite. Coral limestone is bit more stronger than calcarnite, and pores are also lesser in this. Pores are bit more in this. We will look into more on that. Now, as I said, we are doing this design as per British standards, BSEN, British standards as per European norms. These are some list of the standards followed. We had a standard in which general rules, principles of geotechnical design. Then we had a code for following ground investigation and testing, how that has to be done. Then for the seismic part, earthquake design, we had two codes. Now, BSCN, what is the difference between BSCN and our normal Indian standards? In Indian standards, we have something called factor of safety. For example, pile design, we are designing it for a load of 1000 kilonewton, and our factor of safety is say two. If our factor of safety is 2, we have to design a pile for 2000 kilonewton, meaning we are getting a resistance of 2000 kilonewton, that divided by 2000 kilonewton. Like that only we will be designing a pile in our Indian standards. But coming to British standards, we have a concept called limit state design. And limit state design, it is nothing but we are checking two things: ultimate limit state and serviceability limit state. Now, what is ultimate limit state? When a structure is failing completely, like you can see that this wind turbine has fully tilted and failed. And it is a complete failure. When a complete failure of ground happens, that we call as ultimate limit state. But for example, it is just tilting. The wind turbine is standing over there, but it is just tilting, and the functionality, some sort of serviceability is getting affected. That is called serviceability limit state. Here, the tilt angle is exceeding an allowable value. That is what is happening, and that is called serviceability limit state. So, what we will do is we will check for these two things: is the structure actually failing, or is the structure only surpassing the serviceability criteria? So, these two things has to be checked, and whichever is giving a lower pile resistance, that is what we are going to recommend as the pile capacity. Now coming to this BSCN, we have something called as geotechnical category, like considering many things like the risk factor or the structure's relevance, importance, available test results, all these things, we will categorize the structure into each of categories. And also say in a full bridge structure, this category is basically for how much importance or how much attention we should give for the when we are doing the design. Like I will explain to that. Let me take. Okay. So we have three categories. Okay. So geotechnical category one will be small and simple structures which doesn't have any risk. For example, we are constructing a bus stop. Which is on top of a very good ground, so there we don't have much risk. Okay, and it is not a mm, like small structure, doesn't have much load, only people will be coming and sitting, all those things. So residential buildings, such places means we don't have much risk to be considered, which doesn't have much load or which doesn't have something very unpredictable happening. So that will come as category 1. And category 2 are which are done and studied type of structures. For example, a three-story building or a bridge or whatever be the structure, if it is a repeated sort of project. For example, we have constructed some 1 kilometer bridge, and we are going to extend it for extra 1 kilometer. So that 1 kilometer bridge, we already know everything, we know how we did it, we know the ground type, we know the whole design. So designing the next 1 kilometer extra would be very easy, and that will fall into geotechnical category 2. But for example, our this project, we didn't know anything in this whole Maldives area itself. Only one bridge was constructed before, and we don't have any published papers in this particular area. We don't have many studies done over there. When we were taking the ground and testing it, also we were not able to even properly identify what type of thing is there. We are telling it is calcarnite and coral limestone based on some standard published, but then are we really sure? Are these really looking like limestone and calcarnite? All these doubts were there, and coral reefs are there. How we will identify all these cavities? Is there any method to identify cavities? So there is like so much we are entering into a project with so much unknowns. When that is the case, we will go for something called as geotechnical category 3, and it has so many abnormal risk and difficult ground conditions. So what is the difference when we assign all these categories is, if it is just category 1, we can do on a limited control level, and a self-checking would be sufficient. For example, I am doing the design and I am checking by myself and the thing is done. But when it comes to GC2, geotechnical category 2, then I am doing a design and I will ask somebody else, a different organization will come into picture to check that. That is how geotechnical category 2 is done. And coming to category 3, in this particular project, we had three companies checking apart from us who were doing the design. When we do the design, our contractor who has given us the job will check the design. Then we had an independent checker who is also assigned by the contractor as a second checker, and they will be also doing our checking. And finally, client, the Maldives government also has assigned some designer, and they will also do a check. And this person who was assigned, like what happened is two companies were parallelly doing the design. Finally, what we did, the detailed design, uh, we will have three sort of entities in a project. One is detailed design consultant, then we will have an independent engineer, then we will have client's representative. So detailed designer will do the design, independent engineer will also do their own design and compare it with our design, and finally client's representative will be the one who will be checking both of these designs and finally approving it. Okay, this is fine, go ahead for the design. That is how the geotechnical category 3 happens. Now, in this whole bridge, as I said, we have navigational span. You can see over here, the ground level is very deep. So this is navigational span 1. And here you can see the gap between these two piles. But here, see, it is very closely spaced. And for this structure, we will have, this pile is very much critical because it will have the highest load. So like that, we had three navigational spans. And these portions are all marine bridges, and over here you can see these are all at grade stretches. These are all at grade stretches. See this much at grade stretch we had. And we will have ramp also. When we go from the ground level to the higher marine bridges, then we will have ramps. Here also we had a ramp like that. Now this one structure, this is say for example a four pile group, and we are seeing the elevation, a cross section in this manner. Then what all will we have? We will have a pier. This is the bridge running. Okay, so below that we will have a pier, and just above the water level we will have a pile cap. Then piles will be there, and the piles will be embedded into the ground. This is the structure. Now, just to take you through the type of piles and give an idea about pile. So, pile is something which will run through lower density material and take it into a higher density material so that it can sustain some load coming from the superstructure. And we have basically um, two types of piles, which is replacement method. We are removing the soil and putting a pile over there. Then we have displacement, where we will be pushing the pile and driving it into there. So what happens in that method is we are displacing the soil. When the soil is removed, we are replacing the soil with the pile. So these two are different type of piles. So replacement piles are basically called bored piles, and displacement piles are called driven piles. And in driven piles also we have a differentiation like small displacement and large displacement. When a lot of soil is being displaced, it is called large displacement. So when the solid piles is driven, then it will become large displacement. But if a hollow pile is being driven, then it will become small displacements. When it is hollow pile, little bit of ground will enter the pile, right? And only little portion of soil will be displaced. So that is hollow piles. So this is just a demonstration of a how a driven pile will be. This is what I said. We will be pushing into the ground. These are examples of driven piles. And now bored piles, we will be boring. We will be putting a reinforcement cage, and we will be pouring the concrete. And this is how a bored pile is being made. So in our project, we went for bored pile only. Uh, yeah, now let's see how the ground investigation was done. Before doing ground investigation, we should understand stages of project. So initially a project will be proposed. Thereafter a tender stage will be there where the client will be giving out the tender, and who wants to do this design, like that they will be doing a tender quotation. So many companies will apply for that, and whosoever they will have many criterias. Is it economy wise okay, who is giving for the lowest money, or is it that, or who is more experienced in such projects. Client will have so many criteria. Based on that, they will award it to one of the contractors, and contractor will then put a designer in place. And designers will initially do a preliminary design based on the already available ground investigation. And after already available ground investigation, a detailed design will be proposed, which will be finally done in the site. And after all the design and after all the construction, we will do a design validation. For example, we are constructing piles, we will maybe check 1% of the total piles. If 100 piles are there, one pile we will check for the pile capacity. How much capacity does this pile have, like that. Now in this particular project, if we have a 6 pile group, what we went for is we had something called, we will do this boreholes in all of the pile locations. Okay, and we had a classification like pre-drill and probe hole. For example, we did our piling only like, sorry, we did the investigation only in this pink color things. Okay, lab test and in situ test. This orange color was just for identifying cavities. So cavity, as I said, was a major part of this, right? So for identifying cavities, we had something called a destructive drilling. So wherever some sort of we will be drilling, and if the torque is increasing all of a sudden, that indicates that there is no material to resist that. So that indicates a presence of cavity. So such an investigation was done. And how this investigation depth and all was fixed was, we already had some tender boreholes, meaning when the project started itself, we had some boreholes in place which was done by the client, by the Maldives government. So based on that boreholes, we will do a preliminary pile design sort of, and we will estimate the length of pile. And after that pile length is estimated, we will give some extra 10 meter, and for that pile length plus 10 meter is what we will do the borehole depth. That much deep we will do a borehole. Now, what all tests were done? As you all know, SPT was done. And why SPT and not CPT? This is just a general rule of thumb. From my experience, what I know is if it is cohesionless soil, then it is better. They will be sending so many sound waves in all the three directions, and when they send it like that, they will be able to develop a 3D view of how that borehole will be looking. I will show that in the next slide. See over here, you can this is the result of borehole televiewer, and here you can see the shear wave in green color and primary wave p wave in the red color, the velocities. So for different velocities we can sort of identify what is the ground type in each of these depths. And coming to borehole televiewer, you can see over here this ground is not looking very good, right? It is all broken pieces. Same thing is reflected in the acoustic borehole televiewer survey also. We can see some gaps like this. Whichever is highly lighted, like good light is there, that is good ground. Wherever some sort of darkness is there, that indicates a weakness. So that is visible in this core log also. So this is a very interesting test sort of. As I said, with this we can identify the fractures and where our cavities are there, all those details. Now coming to laboratory test, for soil we have something called index test where we will be characterizing the soil. Like is it a sand, is it a clay? Now if it is a sand, is it silty sand, is it clay sand, or is it well graded sand, or is it poorly graded sand? All these things we can find out based on these three parameters: moisture content, Atterberg limits, and particle size distribution. Then we have strength test where we will be measuring the unconfined compressive strength test. If it is a cohesive soil, then we will get the UCS value, means when the soil sample is not confined in three, confined laterally, how much strength it can take axially. So once we find that out, we can understand what is the shear strength. Basically, shear strength is UCS divided by 2. And we have direct shear test where it is cautionless soil. If it is identified as a cautionless soil, we can do a direct shear test where we will get the angle of internal friction value. Then we have, if it is clay soils, we have consolidation test. We will where we will get the consolidation parameters like void ratio and the compression ratio, all those things to identify the settlement of ground. All those things we need these parameters. Now coming to rock also we have the same distinction of index test and strength test, but coming to rock, to identify what type of rock it is, what we need is basically density and porosity. And to understand the strength test, almost similar test like our soil itself is there for rock also. Unconfined compressive strength test, when we do UCS test in rock, we can also measure the deformability, elastic modulus of the rock as well we can measure. Then we have same direct shear test and triaxial test also for rock. Then we have now discussed about the study. We have discussed about ground investigation. Now let's discuss, come to the geotechnical design, our main part. After that, we will look into mitigation measures and pilot test also. So regarding uh, the ground characterization, what we need to do is we need to characterize the ground, right? So for that we have two methods, not two methods. We have to do two things. First will be we have to analyze the distribution of data. How to analyze the distribution of data? To understand the distribution of data, we can plot. Here you can see the UCS is plotted against the elevation of ground. So we understand, okay, fine, this is where the range of UCS is 6 MPa to 12 MPa. We have in this particular portion minus 40 to minus 60. Then we what we can do is we can go with number of tests and minimum maximum of all these values, like that we can check. So once we do these things, we will get an idea. Okay, what is the distribution range? And from this, we have to come with the characterization of the ground. So here we wanted to understand how the shear strength is behaving based on UCS. So what we did is we plotted all the values, and then we checked the literatures and we understood what is the maximum and minimum. Then we came up with the characterization. So what you see in this orange color over here is what we finally used for our design. So based on this, dots are how the ground is behaving at site, and what we came up with is this orange color. We are sort of characterizing based on these results how the ground is behaving. What the problem is, we have results here and there only, right? But then we are doing generalizing the ground as a whole, so we need such characterization to do that. That is what we do with characterization. Now before going into this, I just want to run you through some of the important parameters of this particular project. It was basically SPT, RQD, and UCS. Uh, SPT, I hope everyone knows, 30 centimeter, how many blows are there. RQD is basically this is a 1.5 meter core, okay, rock core. So here we will check how many cores is recovered, which is more than 10 centimeter long. So in this yellow box, so that particular length divided by this whole 1.5 meter into 100 will give you the RQD. So this RQD is giving you sort of the rock quality, how much we can retrieve the rock without it breaking. Then we have UCS test. So here, as I said, the unconfined rock sample will be pushed from top and it will fail in this fashion. And how much compressive strength it could take is basically the UCS value. Now, based on all these test results, we divided the whole ground into four units: Unit 1, Unit 2, Unit 3, and Unit 4. So, from here, visually, what you can look into is these are all looking like sand, right? Broken particles. This we called as the first unit, Unit 1. Then, if it is like bit more bigger pieces, then we called it as Unit 2. And whatever we could retrieve a solid course. It didn't break like this, and it was a solid cylindrical course. That will be either Unit 3 or Unit 4. So, Unit 3 was whichever had UCS in range of 0 to 10 MPa, and whichever was more than 10 MPa, we classified it as Unit 4. And unit 1 and unit 2 we had a distinction of shear wave velocity also. I have talked about shear wave velocity right in previous slides. So if it is more than 800 then we called it as unit 2, and if it is less than 800 we called it as unit 1. So this 800 meter per second is a distinction value for rock or soil. So if it is, although it is broken, what we believe is it was broken due to the sampling process, and in actual it is an intact rock. So that's why the shear wave velocity came as above 800 meter per second, and we called it as unit 2. Now I will show you an example on how we see this is the distribution of all the UCS values, okay? And maybe the average will be somewhere over here. Average is the value where 50 percentage is below and 50 percentage of values are above. uh, Average, or you can call it as median value. So that might be somewhere around 3 MPa, and a value we took was just below that. Because the distribution is this much high, we can't just go with average. It's better to be on a conservative side. By conservative side, we are being on a safe side. So for that, we went below average. Now I will talk about few things what we need to be aware of while we are doing a pile design basically. So first we need to understand how the pile is behaving. Is the pile behaving as a group? When we have group piles, I think you would have studied about it. Pile, individual pile action and pile group action. Is the pile group behaving as a single block pile group action, or is the individual pile relevant? So basically this difference comes based on the spacing. If the piles are widely spaced, then an individual pile action is more prominent. But if it is closely spaced, then a group action is a bit more prominent. Now coming to another thing which we need to be aware of is loading duration and variation. So are there any temporary loads? Like what all loads are going to come on a temporary basis during construction? Then what all are the permanent loads? Then also we should think about overburden and groundwater. Is there any chance of any overburden coming in future, or how much the tide will be varying on a day-to-day basis? Like maybe after 100 years, what will be the tidal level? Such things we should check. Then we have a choice of pile type, like ground type, based on, like I as I said before, we have bored pile and driven piles, right? So that we should decide based on ground type. Like here what happened was we had so many coral reefs, right? So if we do a driven piles, that will be hammering action and so much vibration will pass through the ground, right? So that will be bad for the coral reefs in the Maldives island. So the government itself suggested that you should do a boring only. So in boring, we will be like very softly sort of removing the ground in that bore portion and then filling it with the concrete and reinforcement. So that has minimal disturbance compared to driven piles for the ground existing over there. Then we have stresses during pile installation. Like as I said, now driven piles will have more impact, so that's why we went for board piles. Then effect on adjacent structures as well as handling. What type of pile will we be able to do at site? Is driven piles easy to do at that site, or board pile? Sometimes the site will be very much isolated that you won't be able to cast in situ, like sorry, you won't be able to factory make the piles and take it to the site. And coming to cast in situ, you should have like sufficient space and the time duration, like where you will be casting the concrete, and you should be able to take it up to the site, and by that time nothing should happen to the concrete made. All these things, so many things has to be thought before coming up with the choice of pile type. And while designing pile, it is not always just putting some values into the input into the equation and coming up with the pile resistance. We have to think of multiple things when we are doing a pile design project as such. Then some additional consideration is pile spacing and type of installation also. Um, Okay, then while doing concreting, will there be any local instability? Sometimes, when we have cavities, what will happen is if that cavity was not identified before, and the boring will we will be pouring concrete, and the whole concrete will be getting lost through those cavities. So such things, if we are aware before going into that, we can somehow prevent all these things. Now, for doing vertical pile design, we have empirical methods that you would have studied when you learn the pile design. So, like this cautionless and corrosive soil formulas you would have seen, right? So, that is basically empirical methods. Then we have static pile load test, where we will be testing the pile at side, and also we have dynamic pile load test. These two pile load test results will give us the pile capacity at the site. This pile, how much load it can take for a particular deformation or so, we will get the pile capacity, and through empirical methods also we will get the pile capacity. So these are some of the design methods. How will this become a design method is basically, if we will do a sacrificial pile sort of, like similar construction method, similar dia, similar ground type, we will do a pile just for the purpose of testing, and we will understand how much capacity it has. And when we do a similar pile for the working pile, like the final pile, if we do a similar pile with same dia, same type of concrete and same type of ground, we can for sure um, confirm that that pile also will have same capacity, right? So that is one of the method, but it is a costly method. We can't keep on constructing many piles and checking. So that is where we have these empirical or analytical methods to find out the pile capacity. Now this BSCN had a difference. As I said, Indian code has factor safety, right? But what we have in BSCN is something called partial resistance factors, where we have different factor of safeties for base capacity, skin resistance, and for tension. And then BSCN means it is a British standard European norm, right? For different locations, like say Denmark, Norway, we will have an extra factor based on that site's situation. For example, for this Maldives, what we used is 1.4. But for say British, like England, we might have to use only 1.2. So what is this 1.4 and 1.2 is, this 1.4 will be multiplied with this 1.4, and that is what the final skin resistance factor will be. Similarly, base resistance of 1.7 will be multiplied with this 1.4, and that is what we have to divide the ultimate end bearing capacity with to get the safe bearing capacity. Yeah, and I want to take you through how we did the design of the pile. Okay, so what you see over here on the left hand side is the borehole behavior. The borehole behavior we have shown over here. So this peach color is unit 3, this red color is uh, unit 3A, 3B, and this is unit 2, this is unit 1. Yellow color is unit 1. Okay, so like this, we have a distribution of ground over here, and what we will do is we will make such rectangles. Okay, and like where the ground is behaving in a similar fashion, and we will come up with a characteristic unit finally. So based on all of this behavior, you can see that this peach color is very much frequent, right? And this inclusions of violet and red, these are stronger soils, but we don't have it much everywhere. It is just distributed, scattered here and there. So we can't take it as that. What we can take the behavior as for being on a safer side is this peach color, which is unit 3A. Uh, Now we will see about the mitigation measures. Here, no ground improvement was required as such. We just had reclamation here and there. Then for liquefactions, cover and erosion, what we did is, uh, we will identify what is the scour level and active movement will be there between pile and soil, and that is how the pile capacity is being forming. So if there is a deflection, if there is a deflection from the soil and the pile, there won't be any friction and there won't be any skin resistance. So it is basically to reduce the skin resistance by a factor until the fixity level, especially when the pile is in marine conditions and so much freestanding length of pile will be there. Freestanding meaning the pile portion in above ground. So in such situations, the deflection will be high, and this sort of reduction up until fixity level is something we should be cautious about. So that also was done over here. Um, yeah, and if liquefaction was there, liquefaction also was ignored. Thereafter cavity also, if there that was ignored. So what we did is we measured the total length of cavity up until the pile length, and that was added at the end. That much extra pile length was given. Then we had cyclic loading, which I said about the pile deflection until fixity level, and we reduced the skin resistance. Then scour ground resistance was ignored. Now we looked into all these things, and finally we have the pile load test. So here, bidirectional pile load test was done, and what we will do is we will put a load cell at a particular depth where below the skin resistance plus base resistance will be equal to skin resistance above this. So we will be putting a cell over here and loading it in two directions, and we will find out what is how much skin resistance is there in each of these layers. So when we found out like that, see over here we took some 250 kPa for design, or over here we took 109.5 for design, and finally we got some 374 kPa. So we are validating that our design value is fine. And over here what happened was, and the pile, um, something is there like the values what we measure will be, we can use it only if the resistance goes above, reaches a peak, and it will mobilize into a straight line like that. If it doesn't mobilize in that fashion, it indicates that the pile has not reached its ultimate capacity. So over here you can see that difference. This is unit skin friction versus the movement plot. Okay, so the pile is moving, but what is happening, pile is moving or pile is displacing, that is pile is deforming, that is the correct terminology. So that is happening, but what you can see over here, it is not mobilizing and it has not reached the peak value. So some more threshold resistance is there inside the pile which we were not able to test out, but maybe for this layer alone we were able to do it because it reached the peak and it mobilized sort of. Mm, Okay, and something interesting in this project and which was a bit different was how we estimated the lateral pile design. Uh, so for getting the lateral pile behavior, we have something called PY curves. Okay, so what it is basically, for a particular P value, that is lateral pressure, how much lateral displacement will happen in the pile. So such curves we will have for different type of soils, and using that behavior, P and Y behavior, we have some such curves, P and Y behavior curves we will have. And this behavior itself we can input in structural softwares like midas, and that is how we will be simulating the soil in their softwares. So this is something like how, if you think about how we will be doing the design for structurally and how we will simulate the soil. So basically what happens, as per my knowledge in the industry, is we have different softwares for structural design and geotechnical design. We don't have an integrated software as such. So structural softwares won't have the ability to actually model the soil characteristics, while the geotechnical softwares like taxes and all can't properly model all the structures. we have to go with some assumptions or some such things. So such an assumption used by structural designers for modeling the ground behavior is what I'm explaining now is called PY behavior. Like what they will do is at each of the depth they will tell the software like if the if for this lateral displacement is happening, this is the lateral pressure or capacity at that particular portion. For example, due to structural loads, if the pile is moving by 5 mm, the lateral capacity to be considered, the lateral resistance which the soil will provide is 110. So that is how we will model the ground in the structural software. Now these are some of the geotechnical risk what we faced in the project, like variable strength. If you remember that initial picture of some calcareous sediments what I showed, some portion will have cavities, some portion will have good rock. So and even that distribution of design profile I showed, right? Hmm. Mm, yeah. So here you can see such a distribution is there. Pile is not at all behaving in an uniform fashion. Here and there we have different type of scattered behavior. So that was a huge risk factor in this whole project actually. Um, Then we had low density and brittleness of reef limestone. So this particular reef limestone will be breaking. It was not a proper what you can say shear strength failure sort of behavior. It was a brittle in nature. So that was one risk factor. So what we will do was we will give higher factor of safety to be safe regarding that. After applying all these partial resistance factor, we will give some extra 5 percentage or 10 percentage extra pile length to be on safe side. Then we had possibilities of cavities, unpredictable cavities. So what we did is we don't know what is happening below the pile tip, right? So it's better to ignore the end bearing because first of all this pile was very long and we when it is bored pile under water, it is very difficult to ensure a proper end bearing at the bottom. Also, we had a risk of cavities below, so we were not fully sure how much end bearing the piles can give. So when we started the design, we decided to ignore the end bearing and that. But when we did the pile load test and all, end bearing was mobilizing in actual. But to be on safe side, when we started the design, it was better to ignore the end bearing. Then the reef limestone, if you remember the ground profile, it was very much irregular. Then, like because cavities were there and because of this much variable strength, we ensured that a pile, like a borehole, would be done in each of the pile footprints. Yeah, thank you.
Thank you, ma'am. Participants, now this forum is open for discussion. If there is any queries or clarification, you can ask.
Good morning, ma'am.
Good
I'm
morning.
Dr. Ananda from Sedu Institute of Technology.
Okay, hi.
Ma'am, nice presentation.
Thank you.
I already having a exposure of onshore and offshore experience in Saudi Arabia.
Oh, nice.
It's a power plant project. We work for the bridge construction work, like the same pile concept.
Okay.
but I am not involved in design.
Okay.
I'm involved in the construction parameters.
Mm-hmm.
Okay. This is the session. I'm really interested to get the ideas. What are the factors of design, and what are the factors we have to consider while in the design parameters. Okay. Another
Understood.
question, ma'am. It's a very good manner. We are face the difficulties in inclined pile boring and pile construction.
Mm-hmm.
In the vertical, it's very easy to provide. If you are providing the angle, it is
Mm.
very hard to execute.
Mm.
That is
Yes,
the
yes.
problem faced in the actual execution time.
Mm.
Like the pile also, we are made a testing pile also.
Mm.
Before the casting, we gone for a testing pile.
Mm-hmm.
This is the what we done, but
Mm.
actually we are not having idea about the design parameters. Okay.
Okay, okay.
Uh, Thank you for the
Like,
session, ma'am.
yeah. Anything I should show you regarding design parameters? The shear
Um,
strength value which was used for our design is there in this particular slide. If you see for each of
mm,
the type of soils, I didn't go in much detail respecting the time limit. So you can see
yes,
what
ma'am.
all are the skin friction values used for different type of soils. And as you said about that inclined portion, inclined
Mm,
ground, we also had one such pile actually. So we have an option in this L pile software of modeling sloping ground and simulating
mm,
the such behavior. So that is what we did for our design.
okay, ma'am. Okay. Thank you,
Oh,
ma'am.
yeah, thank you.
Thank you, sir. Gauri ma'am, there is a question in the chat section.
Okay,
Can you open it?
okay.
Mr. Amit Kumar has asked four questions.
Could you please? Okay, I got it. Yeah. What was the borehole termination criteria in soil and rock during geotechnical investigation, and which technique is adopted for drilling borehole in marine? Borehole termination criteria was that initially there was some preliminary boreholes or tender boreholes done by the client. So when it came for detailed design, the preliminary pile design was done based on those tender boreholes, and we estimated what will be the approximate length of pile. So once that was ready, in each of the pile footprint, say for example 50-meter was the pile length, we went for 60-meter borehole termination. And drilling borehole, uh, which technique was adopted for drilling borehole? Actually, I don't remember it exactly. um, Fugro has done the marine borehole investigation for this project, and I can share my mail ID. I can look into it and maybe send you what was the investigation drilling technique. Then at what depth rock encountered from seabed? Actually, here, if it was land, then we had some 20 meters of carbonate sand, and then only rock was encountered. But if it is marine, then from the seabed level itself, there was rock. But the problem was the rock was not strong throughout the depth. In between, there will be cavities, or in between, there will be carbonate sand or carbonate gravel inclusions. How many boreholes are done in the seabed span of 3.5 kilometer as mentioned? We had some in this whole span of 6.7 kilometers, there were 68 piers. And in this 68 piers, some were two pile group, some were four pile group, and some were six pile group. And throughout, we had almost 200 boreholes done. Like in each of the how many ever piles are there, that many number of boreholes were done. So there was no distinction as marine or land. If a pile is there, a borehole was done at that location. What is the pile length and dia and rock embedment depth in rock? So pile length, okay, the dia range was 1.5 meter for land piles, 2 meter for shallow water piles, and 2.5 meter for deep water piles. And wherever the load range was 2000 to 4000 ton range, and basically when the load is high, the dia was increasing, right? So when we think in that manner, almost 50-meter embedment was sufficient to for 1.5-meter pile, maybe 1000 ton is the load, so 50-meter embedment. But 2.5-meter pile, when 4000 ton is also there, we are making it 2.5 dia, right? So for that also 50-meter embedment was fine. So that is how the dia and pile length distribution was there. Yeah, I think I answered all the questions. Only that drilling borehole, I will come back to you.
Yes, ma'am. Yes. Thank you. Is there any other question from the participant side? I think there is no other questions or discussion. So, ma'am, thank you for the elaborate and you stuck on with the time. Thank you so much.
Thank
You
you.
almost you gave all the details that was necessary and required. So
Thank you.
again, on behalf of the participants and the Department of Civil Engineering and Veltech Institute, I extend my heartfelt thanks to you, ma'am. Thank you so much.
Thank you.